Hello everybody. In this video we will discuss acid catalyzed hydrolysis of amide reactions. So let's first discuss what is an amide. An amide is when you have this functional group, to be precise, CON. When you have this situations here, that's an amide functional group. Again, the N does not have to have two hydrogen. It could have more carbon chain as well. It could have carbon chain here, one hydrogen here, or both of them could be carbon chains. Okay, so just key idea here is nitrogen has 3 bonds. So if both of them are carbon chains, so here it's connected to 1 chain, 2 chain, and 3 carbon atom, 3 chains. This is called tertiary amide. So this is our tertiary amide. And if it's connected, oh, this is not CH2, this is CH3. So if it is connected to 1 chain here, if it's like this, it's connected to 1 carbon chain to the right, another carbon chain to the left. So this is a secondary amide. Okay, and the one we have here is a primary amide because nitrogen is connected to only 1 carbon chains. Okay, so this is an example of acetamide. Okay, so what would happen when we have hydrolysis in acid catalyzed reactions? So amides are not very reactive group to begin with. So if you want to have a nucleophile, it needs to be catalyzed with either acidic conditions or basic conditions. So let's begin. So in acidic conditions, let's write our proton as Hb plus. That means you have ton of proton. The proton is attached to a conjugate base. It could be H3O plus or something else. Anything that has a proton. So we know, okay, let me delete this yellow thing. So when you have proton, the most basic center is here. This lone pair is the basic. It will immediately abstract a proton. Okay, so let's do it. So what would happen? CH3, C, O, H. So that's, oh, come on. I was trying to do the color here. Let's see. Let me draw everything out first. Okay, so we got this and we have added H. So you noticed oxygen now has 3 bonds. So by our shortcuts that we have been using, when you have 3 bonds, it should have a positive charge. 2 bonds, like here, oxygen should be neutral. If you have 1 bond, then oxygen would be negative. Okay, so here we have positive centers. Now at this point, there are a couple of things we can do. So every time you see a positive charge on your oxygen or nitrogen, so your next goal should be neutralize it. How many ways you can neutralize it? So if you want to neutralize it, you need a pair of electron. Well, I could get a pair of electron if I bring these 2 electrons here back to oxygens. And if I do that, that's basically I'm taking out my hydrogens. I'm taking out my hydrogen out. Well, not with the electrons, but without the electrons. So these 2 electrons would neutralize the oxygens. So oxygen is this. So basically you're going backwards. So you will see every step in this reaction is gonna be equilibrium. So you can go either way. Okay, let's bring that there. So let's do something different. So what if I move these 2 pair of electrons towards oxygen to neutralize it? If I do so, so you noticed I am losing a lot of electron from carbon. So carbon become highly positive. So by bringing the pi electron towards oxygen, we are increasing the positive charge on carbon atoms. So now if I do that, I'm essentially creating a positive charge here. Okay, so that's the idea behind it. So I will do that. Okay, so by protonating the oxygen, we are increasing the electrophilicity of carbonyl carbon. So that's how it's activating the amide function group to react. Or essentially, that's basically easier way to say is it's making the carbonyl carbon more positive. More positive. So what happened when something gets more positive? The nucleophile would be able to attack. So in this case, our nucleophile is basically on water. So the water is our nucleophile. So that now the nucleophile will come and attack on this carbonyl carbons. Okay, so if we do that, what we will make? We will make CS3COH, NH2, and now we have OH. So again, oxygen has 3 bonds, so it should have a positive charge. Look at the carbon atom. Now it becomes sp3 hybridized carbon atom. So this is our sp3 hybridized carbon atom. And when something is sp3, that's our tetrahedral. So this is called tetrahedral intermediate. And we're going to get 3 of these. Let's call this 1, tetrahedral intermediate 1. Next goal, when you have a positive charge, it should be to neutralize the positive charge. A couple of ways you can do it. I can neutralize the positive charge by bringing these 2 electrons. If I do that, that's basically going backward. But let's do something different. So remember, we just created our base here. So there was B here. So anything that could abstract a proton, so which is in this case B, would abstract the proton from this positive centers. And we will draw our next intermediate, CS3COH, NH2, and now we have our OH. Okay, so now at this point anything can get protonated, but the nitrogen here would be slightly more basic. And let's say we have a lone pair here. So we just had our HB plus. So let's say nitrogen abstract this proton, because if any of these oxygen abstract a proton, then that's basically going backward. So let's say the nitrogen abstract the proton. Oh, by the way, this is our tetrahedral intermediate. Tetrahedral intermediate 2. We're gonna get 3 of these. That's how you know if you don't have 3 of the tetrahedral intermediate, you did something wrong. Okay, so now when we protonate this, we will get CS3COH, NH2. Okay, I'm gonna draw out the whole NH2 for a reason, to show you something. Okay, so nitrogen, by our shortcuts, should always have 3 bonds. So here it has 3 bonds. Before it has 3 bonds. So every time it has 3 bonds, it should be neutral. When it's give away electron to make 4 bonds, right, like here, it should have a positive charge. So I'm going to add a positive charge here. And obviously we had OH. And when you do that, what would happen? What should be our next goal? Next goal should be to neutralize the positive charge on nitrogens. I can do that by getting rid of my proton again. So by bringing these 2 electrons, so that's basically going backward. Okay, so move on. So we can neutralize the positive charge on nitrogen by breaking this bond here. So I can break this bond here. I will bring these 2 electrons back to nitrogens. Okay, so if I do that, look what happens. So let's say both of the electron is gone. So you noticed carbon does not have octet anymore. It has lost an electron, so it should become positive. But simultaneously, because oxygen has electron also, it will say, oh, carbon, you seem sad, you don't have electron anymore, so here's take some electron. So either one of these oxygens immediately will provide the electron to keep the carbon atom happy and octet. Okay, so let's draw it out. Okay, I will bring them back here. So what we did here is we neutralized the positive charge on nitrogens. simultaneously one of the oxygen, again, anyone can do it, one of the oxygen can provide the electrons. So what you will get is, CS3COH. Oh no, we are supposed to draw in pink. Okay, so what we would get is CS3C double bond OH. So nitrogen is gone, so we got NH and H, and we got the lone pairs. And then on the bottom we have our OH. Okay, so you noticed here oxygen has 3 bonds, so it should be positive. And what should be our next goal? Our next goal should be to neutralize the positive charge on oxygens. So in this case, we will abstract the proton. Now somebody would abstract the proton. It turns out because ammonia is one of the most basic lone pair you will find out in the reaction. So ammonia is the most basic things that you will have in your reaction at that point of time. So that's the one gonna immediately abstract the protons, right? Because it was nearby, and it will immediately abstract the proton. And also ammonia cannot stay on its own if you have ton of proton. So ammonia will get protonated as soon as it has a proton. So in this case, this is a proton source. It will immediately get protonated. So you will make CS3COOH plus NH4 plus. So those are the two products that you will be making. So you're going to make carboxylic acid and you're going to make NH4 plus. So in shortcuts, like basically what did we do here is we added, oh, this is here. So basically what we did here is we broke this bond and we added water across it. So we added OH here and H here. And because it is an acid catalyzed, we added another extra H. And that's the reactions. Pretty simple and fast. All right, let's stop this video here.